Very good evening to you all. For those of you I haven't met yet, I'm Gretchen Larson. I'm one of the co-directors of the Institute of Advanced Study, and I'm a professor of marketing here at Durham University. I have the pleasure of chairing tonight's lecture. But before I introduce our distinguished speaker, I would like to extend a very warm welcome to you all, and thank you for coming along to what promises to be a really fascinating talk. I'd also like to take the opportunity to say a few words about what we do at the Institute of Advanced Study. So we are a home for growing big ideas. We support a broad and inclusive interdisciplinary community from across the full spectrum of Durham academics, where different perspectives are brought together to develop creative approaches to interesting and important problems. And to this end, we fund and support several major projects each year that focus on interdisciplinary, innovative and ambitious research projects. These also provide the opportunity to bring in fellows who play a key part in these projects. And incidentally, our call for major project applications is just launched today, so if you're interested you can find out more information about this on our website. We also fund smaller development projects, and we support a network of associate fellows. And a key part of our activities are our series of lunchtime seminars and public events by our fellows, which is why we're all here this evening. So tonight's public lecture is by our fellow, Professor Ramesh Subramaniam. Professor Subramaniam is a senior professor at the Department of Physics of the Universitat Malaya. He is a materials scientist well known for his outstanding scholastic contribution on solutions for energy storage and harvesting devices for clean energy and sustainable smart cities of tomorrow. Professor Subramaniam's scholarly eminence has been recognised in his field through many international and national awards. The list of awards is long and includes being selected as a World Academy of Science Young Affiliate Fellow in 2009, and receiving Young Scholar Awards from the American Chemical Society, the International Union of Pure and Applied Chemistry, the IAP, and the Global Young Academy. He was elected as a Fellow of the Academy of Sciences Malaysia in 2016, and a Fellow of the Royal Society of Chemistry the following year. In 2020, he was in the world's top 2 scientists for career-long citation impact. Actually, the top 1.2%, I believe, so quite incredible, and this is recognised by Stanford University. So Professor Subramaniam is a recipient of a Fulbright Fellowship with a tenure at Princeton University as a visiting fellow, and we've been lucky enough to have previously hosted him here at Durham University as a recipient of a Senior Durham International Fellowship for Research and Enterprise. During this visit, Professor Subramaniam is collaborating with Dr. Paul McGonigal from the Department of Chemistry and the Functional Molecules and Materials Research Group on energy storage devices for smart, sustainable cities. His research fits perfectly with energy and clean growth, which is one of the 5 university-wide research themes at Durham. He is also collaborating with energy economists to compare economic efficiency of energy-efficient vehicles and internal combustion engine vehicles, considering both economic and environmental perspectives. The topic of tonight's talk is Beyond the Tipping Point, Energy Storage and Harvesting for a Sustainable Future. So please join me in giving a warm welcome to Professor Subramaniam.
Thank you very much for your kind introductions. So I'm Ramesh Subramaniam from University of Malaya, Malaysia. The talk today is going to be on Beyond the Tipping Point, energy storage and harvesting for a sustainable future. As per the introduction, you know I'm a material scientist, so the talk more towards the materials regarding how to, we formulate and characterize and fabricate the energy storage devices and also the energy harvesting devices. I may not go very details about the technical part, but I'll try to give an overall view so that people from a different discipline still can follow the talk and know what they are doing. Okay, first of all, I want to start with the motivation for the work. As we know, the 2019 Nobel Prize in Chemistry for development of lithium-ion batteries. So when I started my PhD work, we work on the lithium ions, and mostly for energy storage devices like batteries and supercapacitors. So now we already, can see there is a Nobel Prize given for the development of lithium-ion batteries. So this is one of the energy storage devices are well recognized. So what is the next? So what are the drawbacks about on lithium-ion batteries? So how to make the things even better? So that is one of the main focus on our research. And then there is 10 prediction for the next decade was published in one of the main sources here, the world in 2030 by Capital Group. So this is the economic group. So among that 10 prediction for the next decade, so the three highlight that I put it here is one is the autonomous vehicles will hit the fast lane. Second is the green machines will rule the road, and renewable energy will power the world. So why we are focusing on these things? So when we talk about the energy storage devices and energy harvesting devices, we are also focusing on the applications. So here, some of the industries that we are working are on electric vehicles and also the hybrid vehicles. So that is why the focus will be there, because the device that we fabricate need to have some kind of applications so that the continuity will be there. Okay, here, then we talk about the two cities here. One we can say like a sustainable city, and the other one we can see very crowded. So every one of us surely wanted to live in a very sustainable cities. So to make the cities sustainable, so we need to focus on many important things. So what are the sustainable smart cities when we're talking about this? So you can see here, cities with the parks, green spaces, solar powered buildings, rooftop gardens, and good quality of life, space for nature, eco-friendly public transport system, and incorporated with the solar energy usage where it comes to energy harvesting. So in this talk, I'm going to talk about the energy storage and energy harvesting and how to integrate both the devices as well. Okay, how are smart cities related to our work? Okay, these are some of the brief introductions. So you can see our focus is on transport system, specifically on energy storage system for electric vehicles. So not only electric vehicles, and also we are focusing on the hybrid vehicles. So the focuses are on three dimensions. You can see here. We talk about the sustainable cities and electric vehicles and hybrid vehicles. So we need to focus in terms of economic, social, and also environment. So our target, you can see the environmental and economic aspect of smart sustainable cities to reduce air pollution and carbon dioxide emission and create job opportunities. Okay, there are three important drivers that promote the investment in energy storage. Because now we know a lot of funding is becoming more difficult, especially after the COVID-19. So it's not easy to get funding because the government wants to focus more on other things. So, but when we talk about this kind of things, you can see increase in electricity bill, growing dependence on fossil fuel, and decarbonization. So all these things makes the drivers to promote the investment in energy storage devices. So when we talk about the energy storage devices, I mentioned earlier about the Nobel Prize got from the lithium-ion batteries. So here, a very important diagram here you can see here. So a lot of energy storage devices, especially in electric vehicles, we always use batteries. So when we talk about batteries, we focus mainly on lithium-ion batteries. And what are the drawbacks on lithium-ion batteries and fuel cells and compared with the supercapacitors? So we can see here clearly. So the batteries and fuel cells generally will give you like a high energy density. But the problem with the power will be always lesser. So to compromise this, for example, we use supercapacitor. When we use supercapacitor, it's opposite problem will occur. The power density will be always very high, but the energy density becomes low. So some of the electric vehicles company in Malaysia, what they're using is they incorporate both batteries and supercapacitor so that can get a compromised value of the energy density as well as the power density. So we can see there is a huge gap between supercapacitors and batteries. So that is where we are trying to propose a new type of energy storage devices which is known as supercapacitor. So our group is one of the pioneers working on the supercapacitor. So from the name itself we can say this is for supercapacitor and for the battery. So this is supercapacitor. So this supercapacitor will have the compromised property of both batteries and supercapacitor as well. So we hope this can bridge the gap between the supercapacitor and batteries. Some of the basic fundamental of these things, I won't go very details. So this supercapacitor is actually asymmetrical energy storage devices, where one side we have the battery type electrode and the other side we have the supercapacitor type of electrodes. So you can see the battery type electrode generally will be the binder free electrodes. The binder normally used for battery type electrode is a PVDF. So polyvinylidene fluoride. This polyvinylidene fluoride is naturally an insulator. So that is what they use as a binder. So but by not using the binder, even we can get a better performance of the devices. So that will follow the Faraday reactions. The other side will be the capacitive electrodes, where we use the electrostatic reactions. So these work in a combination of different charge storage mechanisms. So you can see the binder electrode. So the property you can see, they increase the ion electron conductivity. They can also increase the rate capability and improve the mechanical properties as well. The other important property of these binder-free electrodes, they can reduce the dead weight. So when we say the dead weight here is a PVDF. So because we are avoiding to using any polymer as a binder. So that's one part. And the electrolyte part later I mentioned more in details. We can use like different types of electrolyte. So I will focus on that later part. So the electrolyte must be safe and no fear of electrolyte leakage. So I'll work more about the formulation of the electrolyte and also the electrode. So both the part I will cover later part. And also another beauty of this supercapacitor is we can be constructed into design whether we want a rigid or flexible. So if we use like a carbon cloth as electrode materials, then we can have a flexible energy storage devices as well. Okay, this part is regarding the country where I live, Malaysia. So you can see Malaysia's carbon dioxide emission in 2020 increased at 69% compared to year 2000. And from that data, we can see the 4 important sectors that emit carbon dioxide. One of the main things is the transport industry. So how can we contribute to reduce the carbon dioxide emissions? So one of the ways is by using electric vehicles. But the main problem with the current electric vehicles is it takes nearly 4 hours to fully charge. And also this is powered by lithium-ion battery technology. So the problem is the time taken and also the distance. So how long it can travel. So this always put us down. So we always opt to the traditional cars. So this is the problem here. So that part I already explained to you. So the energy storage devices can be incorporated with the energy harvesting devices. So these are another things that we are proposing, and we already made some device as well. And energy harvesting devices, when we talk about here, this is mostly on the solar cells. So for the solar cells, you can see we got like a first generation solar cell which focus on the wafer based silicon, and second generation solar cell focusing on the thin film, and the third generation is a new emerging technology. So you can see here got many types of the solar cell, and one of the important things here is a quantum dot solar cell. I'm sure many of you heard about that, but the problem with the quantum dot solar cell is the efficiency is very low. So it's very difficult to get high efficiency. So in our group we are focusing more on the dye-sensitized solar cell. So this dye-sensitized solar cell can give efficiency up to like 10%, and the cost is very low and also easy fabrications. So the energy harvesting device that we are focusing in our group is more towards the dye-sensitized solar cell. And next I also want to focus on the national automotive policy in Malaysia. So one of the main thrust area is energy efficient vehicles. So when we talk about this, one of the main objective about this policy is to reduce carbon emission in line with the ASEAN fuel economy roadmap of 5.3 liters gasoline equivalent per 100 km by 2025. So here you can see the list of technology development projects under these policies. So how the work is very important here. The first one you can see the money or the grant mostly they give for the development of advanced electrode and electrolyte for lithium-ion battery. So that means the focus will be electrode and electrolyte. So these are two main components in the energy storage as well as energy harvesting devices. And then second point is the next generation battery technology. So this is what I mentioned earlier, sir. What is next after battery? How can we overcome the drawback about the battery technology? So that's where I explained to you about the supercapacitor as well as the integration of energy storage and energy harvesting devices. So how is this device related to the policy? So first, of course, it supports the electrification of vehicles in Malaysia towards synergistic benefit on energy security, environment and climate change. And second, we can produce supercapacitor that would have a longer lifetime and longer drive distance. So these two things very important, the time and distance. And to produce novel electron and electrolyte to fabricate supercapacitor, which impacts the automotive industry. Okay, another important thing also I want to share with you all is the impact of COVID-19 on electric vehicles. So the new lifestyle changes of work from home, travel short distances and driving patterns are in favor of electric vehicles. So you can see what are the implications of COVID-19. Because shift away from public to private transport, deurbanization, work from home, shift to shorter trips and predictable driving pattern. So all these things makes electric vehicles higher charge because we're going to come like 5 days work. So you can see the implication also here. Drop in usage of public transport, demand for private ownership of cars have increased post-pandemic, and also remote working has pushed population to move out to the sparsely populated countryside to combat transmission of COVID-19, and longer commuting trips are replaced by shorter trips. So all these are also advantage for electric vehicles. Okay, now we need to get the electrolyte right and the device right for the application in EVs and hybrid devices. So what are the actually issues with the electrolyte, electrode and devices? So even we are using our handphone. All of us are using handphone. And all of us handphones got the batteries. And inside the batteries, these main components are there, electrolyte and electrodes. So even in some of the flights, even like lithium-ion batteries are banned. We know all these things. So whenever you look at the liquid electrolytes, if your batteries are lithium-ion batteries, means the electrolyte will be in the liquid state. So that is one of the important part here. And these liquid electrolytes are harmful and prone to leaking. Sometimes we can see the battery like a bulge and all these things. That's due to the liquid leakage. If you want to overcome that liquid electrolyte, the best will be solid state devices. But again, if we want our energy storage devices, people to attracted to that, it must be in the light in weight. So the best materials to be used in light in weight will be the polymer. But problem is polymers are insulators. So the solid polymer electrolytes is the next thing. But the problem with the solid polymer electrolytes are because from insulator we are making them as a conductor, and also when they are in the solid state, when we sandwich them with the electron, the contact will be an issue as well. So that also we need to overcome. So the contact issues and also the low conductivity. So that's a problem with the low ionic conductivity and narrow operating voltage. So if you look in your battery, if it's written as lithium ion polymer battery, means the electrolyte will be the solid polymer electrolyte. And then we also go for the synthetic polymers because that's a non-biodegradable, because the green technology and so on. When we talk about the electron, the problem I mentioned earlier, the conventional method is electron with binder. So what happens this one? This increases the resistivity and the addition of the dead weight. So we need to come out from the binder-free electrodes. And when we talk about devices, you can see again, I mentioned to you, the problem with the supercapacitors and batteries earlier also. Okay, this is the evaluation of polymer electrodes. The first generation of polymer electrodes, what we call as the salt-based polymer electrodes. So let me give some brief explanation about these things. So in the periodic table, like some basics, okay, in the periodic table, if you see means the first element will be hydrogen, then helium, then lithium. So lithium is the lightest metals. So that's the reason we are using lithium ion batteries, because the weight will be very minimal. So that will be the lithium ion batteries. So for example, even we can see like a magnesium ion batteries, aluminum ion batteries, then the salt need to be magnesium or what you call like a aluminum. Just say the application in, for example, like a solar cell. Like a dye-sensitized solar cell, most of the time they use iodine as the dye. So if you are using iodine, for them to have the redox reactions, the salt need to be iodide based. So what we use a lithium iodide. So the selection of salt is very important here. So that is what we call as salt-based polymer electrolytes. And these salt having the ions. So once these ions is incorporated, the selection of polymer also important, because the ions will be positively charged. So your polymer backbone and the side group must have electronegative groups there. So for example, polyethylene oxide can be used as a polymer host because there is an oxygen group there. Like a polyvinyl alcohol got OH functional group. Polymethyl methacrylate, they got the ester functional group. That's possible. But we cannot use polyethylene or polypropylene as a electrolyte or as a host polymer, because their delta plus and delta minus is not sufficient to interact with the lithium ion. So that is a first generation. But the problem again with this one is the conductivity will be low. So that's where next come the plasticized salt-based polymer electrolytes. When we add plasticizers, what happens? The conductivity is enhanced. But the problem will be they become like too soft, difficult to handle, mechanically unstable. The plasticizers normally they be used like for example like ethylene carbonate, propylene carbonate, phthalates and so on. So to overcome that, we use a nanocomposite polymer electrolytes. When we talk about nanocomposite, these are nanomaterials used to improve the ionic conductivity. They also can improve the mechanical properties. On top of that, these nanoparticles can give a very good aging properties, where they can retain high ionic conductivity with the prolonged times. So these are the advantages of the what we call as a nanocomposite polymer electrolytes. In progressive years, we are also using like the radiation, iron liquid and carbon nanotubes. When we say about ionic liquids can replace the organic solvent. So for example, like a polyvinyl chloride. Polyvinyl chloride normally we dissolve with the tetrahydrofuran, THF. So THF is an organic solvent. But by using iron liquid, we can avoid using organic solvent because they are non-volatile solvent. So it also can, this solvent itself coats the ion state, so which can improve the ionic conductivity. So these are what you call like some explanation about the ionic liquids. So they are bulky cations where they can create more segmental pathways due to their large surface area. And also they can create more amorphous and increases the ion diffusions. And also the addition of iron liquid with the bulky cation will produce high concentration of ions because they itself ions. Okay, next, like I said earlier, from the what I call like liquid electrolyte, the problem is the leakage. Then we come out with the solid polymer electrolytes. So, but the solid polymer electrolytes, we got like the first generation, second generation, third generation, so on, so that the properties are improved. But again, the contact will be always an issue because this is a solid state. So what happened? One of my patient students, he worked on hydrogels, but this hydrogel used for drug delivery. So since the polymers is used as a host materials for a drug delivery, and he completed his patient with that, so then I realized why not we use the hydrogel as a host materials for the energy storage devices, because they have got the highly sticky properties, very flexible, and we can play around with like a toys. So why not we use that? And the beauty of these things is they are stretchable, compressible, flexible, self-healable. This is another important properties. Just say we cut the electrolyte, make like a toothpiece, then we connect them again. They can even show the same properties like previously. So that's another important properties of this. And thermally stable. When we say thermally stable, like the overcharging, the heating can happen. So the temperature can increase. But these hydrogels can absorb the heat. And it can retain the initial properties of the device. So here, this is the mechanical properties of the hydrogel. By using like acrylic acid, you can see we can do the bending, twisting, knotting, all these things can be done with the polymer itself. And these polymers are conducting, and you can see how flexible they are. So I still got a small simple video here, you can see yourself. So you see, we are using a glove, and this is a polymer electrolyte based on the hydrogel. They are very sticky, but still you can play around with these things, you can see here. Okay, so you can see how sticky that is. So this will give us a very good like a contact process when we sandwich with them with the electrode. So we can play around with things. We can do like a few shapes, and they're very flexible. We can do the knotting, can do the U shape without compromising the shape. So that means it's very good for the flexible energy storage devices and stuff. So we can do this knotting as well. Okay, this is hydrogel. These are self-healing properties I mentioned to you. Let's say for example it's a broken, then it can heal and can give the initial properties back again. Okay, regarding more about the hydrogel, I will give the presentation during my seminar in the IAS. So that one more focused on the hydrogel. So next I go for another component of the devices, which is electrode materials. So when we talk about electrode materials, these are the approaches. So we need to focus on the porosity, the size should be nano size, composite materials, doping, and also electrical conductivity. So materials with a nano scale are smaller size and also high surface to volume ratio. So you can see that. So what are the properties of nanomaterials? First, large surface area and also porosity. So you can see this can provide active sites to facilitate the ion diffusion. So that is very important. Second is a good electrochemical performance, and the properties depend on the dimensions. So this one like a 0 dimension, 1 dimension, 2 dimension or 3 dimension the preparation method. So that can vary. So sometimes the problem is the device won't perform well because we need to focus on both the electrode and electrolytes. Then only we can get the optimum power density and the energy density as well. So here are some of the methods that we are using in our lab to work on the electrode materials. So my expertise more on the electrolyte, but now I'm focusing on the electrode as well. So one of the methods is a microwave assisted hydrothermal synthesis. So we are using this method to prepare the electrode materials. So this is a very shorter reaction time and low temperature synthesis, and you can get uniform distribution of particles. So this can improve the device performance as well. And of course save cost and energy and high productivity and efficiency. The latest one we are using for the electrode material is a plasma technology. So one of my undergraduate students, she worked on the plasma technology to work on different applications. So now after discussing with her, we found that plasma technology also can be used to fabricate new type of electrode materials. So currently we are focusing on that, and we got like initial results. So hopefully it can be used as a good device as well. So here, previously I mentioned to you here this part, the composite is very important. So here we can see the what you call like a binary and ternary nanocomposite for electrode materials. So how to make the nickel phosphate and to become as a binary nanocomposite and ternary nanocomposite. So sonochemical and calcination method will be used, and we are using like a polyaniline. The reason is these are conducting polymers. So by using this, the performance of the device can be enhanced as well. Okay, the other new electrode materials that very famously used currently is a magazine. So I'm sure some of you heard about these magazine materials. It is actually there is about 10 years ago they found about these things, and not many research are going on. But now quite a number of review articles, and it really shows better properties compared to other materials. But the beauty of this magazine is we can play around with the combination. They call like a max. So here the M is represent of these functional groups, sorry, these elements, and A from here, and X will be either carbide or nitride materials. So from this combination we can formulate like a new types of magazine, and these can be used as a main electrode materials. And another beauty of this magazine is they can also be incorporated with the tin. Magazine incorporated with the tin also will give a good properties. So these natural resources properties I also will explain in the seminar as well. Okay, here is another just a short video also. So you can see this is one of the hydrogen electrolyte we fabricate, and this is a bare electrode. This is an electrode with a binder, and these are binder-free electrodes. So you can see these are very uniform, and normally the binder-free electrode will give us a very good properties. So this is a device fabricated in the superconductor. So we exhibited this in a few exhibitions, and we got some good remarks and word as well. So you can see, okay, that is it's a very sticky one, and once we sandwich them, that is the casing. You can see here. This is a casing that we use, to fabricate the energy storage devices. I mentioned about the part. So you can see here, so you can see how easily it can bend, and without it breaking, it's not breaking at all. So then that is the electrode materials. This is in the lab scale, so we can do in a bigger scale as well. Then you can see all this information. But normally this one will be done in the glow box. But just for this one, we're just showing it outside. Okay, that is a whole thing, okay, sandwich. Then the casing will be done and put inside that. Okay, this is the casing, like I mentioned to you earlier. So this one got like a US pattern also, we got this one. So the main advantage of this pattern is, this method is one of the most cost efficient ways to connect internally to avoid using any external wires or circuits. So you won't have any external wires and circuits, which eventually maintain the internal resistance of each of the packs. So one of the important companies we supply the electric scooters in Malaysia using this casing. So this is to be patented together with our industry partners. Okay, the other one I also wanted to explain to you is the all-in-one configurations. So I'm sure you learned about and we studied and we heard or read, we prepared the electrolyte, then we prepare the electrode, and these electrode materials will be used as an anode and cathode, then we sandwich, then we produce in the device. So this is another interesting method also. I'm sure some of you would have heard this one. It's called as an all-in-one configurations. When we say all-in-one configurations, so when we fabricate, when we look at the film, it's very difficult for us to differentiate where is the electrode and where is the electrolyte. That's what we call like all-in-one configurations. So we already prepared one sample and what we call like a research work, and now we are in the process of patent the method as well. So maybe I can share with you one of the work we did. It gives rise to the idea that all the components of a device will be one piece materials. I will show the sample also. For example, here we have electrode and electrolyte both in a single hydrogel film. So this can be done because it's a hydrogel. If you're not hydrogel, it's difficult to do that. Because normal film you cannot do, normal polymer film difficult to do. But once we make them as a hydrogel, this is possible. So this gives rise to a non-laminated configuration and helps the device to be very flexible. And no different layers of electrodes and electrolyte and no separator. So normally we also use a separator because the electrolyte, the polymer electrolytes, not only behave as electrolyte, they also behave as separators. But this method can give us the all-in-one configurations. So this is a simple method. I will just explain briefly. So here we use a polyvinyl alcohol and agar. So first step is we make them as a solution. Once we make them the solution, we make the film. And soaking in sulfuric acid and adding glutaraldehyde. So these are like a cross-linking agent, all these things. So this can create a hydrogen electrolytes. Once we get the hydrogen electrolyte, we add the aniline and pyrrole. So this aniline and pyrrole is an electrode materials. So they will polymerize the PNE-PPY electrodes on the hydrogen electrolytes. So once they polymerize on the surface, we will get a sample of this. So this sample you can see, we can roll, we can this one. Actually, this is a all-in-one configuration where electrolyte already on top of the electrode itself. So we cannot differentiate the layers. Like you already had to grow in one thing. And we already published in a good journal, and now we are trying to patent the method as well. So you can see the deposited polyaniline polypyrrole electrodes on the PVA agar hydrogen electrolytes. So all together. So this is what we call as all-in-one configurations. Okay, the last part is regarding the what we call as a energy harvesting. So previously itself I mentioned the energy harvesting devices that we are focusing is a dye-sensitized solar cell. So again for dye-sensitized solar cell also we got like an electrode and electrolyte, and the electrode here based on the dye we are using. For example, just say for example we are using like what we call iodine as a dye, so the iodine must present here. And this hydrogen electrolyte also can be used for fuel cell, polymer electrolyte membrane fuel cell. But again, if you want to use for polymer electrolyte fuel cells, then it must be a proton conductor, because the byproduct is a water. So then we can use like ethanoic acid or something like that, which called the proton as a conductor. So here are the dye-excited solar cell. So they are cost effective, more flexible, and they can work under low light. So here you can see another thing also. The materials, the simple materials and complex processing. And then complex materials, simple processes. So we are focusing on the dye-sensitized solar cells. Even though the materials are complex, the formulation, everything, but the beauty is simple processing. So that means it can be prepared very fast. So if you know some basics, chemistry and all these things, the formulation become easier. Okay, this is what I mentioned to you about the integrations. So the flexible and portable integrated energy harvesting and storage device for self-powered electronic and electric vehicles. Because sometimes when we use like energy harvesting devices like a solar cell, so like a rainy time and night time we can't use it. So that's a problem. So in Malaysia, I don't know how many of you all come to Malaysia. So you're always welcome to Malaysia. Malaysia is a hot country, and we have a rain throughout the year. Not like here today, the rain throughout, but like a drizzling like that. Ours will come one shot like 3-5 hours, and it's really like a downpour like that. So in our country, like we cannot say there's no sun. Every day the sunlight will be there. So by integrating this one, what can happen here is, like daytime, we can use this integration. It can be used like solar cells. They can generate the energy and can be stored. And nighttime or any time, the energy storage devices can be used to get the energy. So these are integrations. So normally in some of the Scandinavian countries, they do the integration between the wind energy and solar energy and something like that. So now we are proposing this, and we are working on this project as well. And the supercapacitor, which I mentioned earlier, can be connected in series and parallel for large-scale applications, which with the integration with the solar cell as well. And current EVs carry a combination of battery packs and supercapacitor packs which consume space, and also more costly compared to supercapacitor. Because nowadays electric vehicles in Malaysia, they're using both together. Means a supercapacitor as well as a batteries. And also can be integrated into power grid, and demand for 5G technology, and also solid state electrochemical devices enable 3D printing as well. Okay, way forward. So electric hybrid vehicles are better than petrol diesel vehicles in terms of fuel economy, noise and emission. And also the manufacturing cost of supercapacitor will be lower than the commercially available supercapacitor plus batteries with the maximum efficiency, which in turn would reduce the price of electric vehicles. And then supercapacitor can one day be used in electric vehicles towards smart, sustainable cities. So recently we also got a grant, just before I come to Durham, I got a grant from the European Union under the Erasmus project. It's about 800,000 euros, working on the smart cities and the learning network in ASEAN countries. So we got like 4 ASEAN countries and also like 3 European partners from Greece, Italy, and also from Germany. So we're going to work on these projects, and sustainable cities network not only focusing on the research, but more on the policies and some professional trainings, and it involves some development of new process as well. Hopefully, it's a 3 years project. Hopefully, we can come up with some good things. So last but not least, I would take this time to thank my family. They are here as well, my family here, and all my teachers from my kindergartens, and my students and collaborators, University Malaya, Durham University, and special thank to Paul. He's the one who invited me, and Alisa as well. She's the first one who introduced me to Durham University. So without them, I would not be in Durham University now. And IAS, special thanks to Linda, she's busy taking a video for me. Special thanks to IAS and Snow College for giving us a wonderful accommodation. Even my family is very enjoyed. Actually, I've been to Snow College in 2018 for 3 months under co-fund with Alisa as well. So this is the second time. So we are having really a good time. We are inside only 3 months, but it's so good. And friends, and not forgetting taxpayers. Moreover, even like EU partners are giving us like nearly like 4 million ringgit Malaysian, which is a huge money. So without them, we can't do much research as well. So with all that, thank you very much.
Thank you so much. I've learnt a huge amount. It's very interesting. We've got about 15 minutes or so for questions, discussion. So, I don't know. Please, go ahead.
Yeah, so this is a question related to the environment. Disposing of batteries is always a challenge. How about this new technology? What sort of challenges in terms of disposing?
When we talk about disposal, is always a big issue because it contains lithium-ion batteries. So now in Malaysia, Malaysia is a developing country, but here when we went to Newcastle, we met, there is a place where you collect the lithium-ion batteries. There is a collection centers there. But in Malaysia, we have in our main cities, we do have the collection centers. But like those who are staying like in the rural areas, the issues is still there. So I think the policies need to be really clear so that the disposal will be need to be really scrutinized. If not, in future, it's going to be a real problem.
Can I follow up that question? So I think the question is really, how are you going to dispose of these hydrogels? What will happen? What will happen to them once?
Oh,
they
the hydrogels?
Yeah, when
Okay.
they reach the end of their life,
Okay.
what do they become?
Yeah. Our focus on what we call as materials formulation and mentioned earlier, the electrode and electrolyte. So that is why for hydrogel in the lab scale, actually we are using like a polyacrylic acid. So now our focus is for the the project with the industry. We want to use a biodegradable polymers. So when this biodegradable polymers like a chitosol, so we tried the chitosol and also we took with the starch and rice. So this can be made as a polymers. So now we are trying to figure out the method because with the chitosol we can make them as hydrogel, the one very done today. So like a cornstarch and rice starch, this can be made as a hydrogel as well. But how they will perform in the devices is a secondary matter. If these things can be performed, then that will be the best things to to minimize the the environmental effect. Because if now we know the device is not easy. Because even though we said we have to dispose this kind of things, but there need to be like a strong policies from the government. Like even like in Singapore, our neighbor country, even you cannot eat chewing gum in the public. The rules are there. But here in Malaysia, we always football managers, they tell stuff, they put the chewing gum and eat in the football field. But in Singapore, in public, you can't do that. So there must be like a strong policies and strong things for the devices. But as a scientist in our part in the lab, we can focus more on the materials formulations. So we are trying to use more like biodegradable materials. That is why even to dissolve the polymers, we try to avoid using organic solvent because organic solvent are environmentally not friendly. So we are trying to go for the iron liquid. And some of the hydrogel can be used, can use water as a solvent as well. But the problem again, water, when you prepare the electrolyte, they show excellent ionic conductivity. Even you can check on the FTR, spectrum, they show like a very huge peak at about 3,600 per cm. So we know because of that, they show high ionic conductivity. But the problem happens, we take this device and we assemble inside the electrolyte. We use that to fabricate the device inside the glow box. Once you charge the batteries, go to a 4 voltage, something like that, immediately it can drop to 1 voltage. Because water is a good friend for ionic conductivity. But when you go to the device, they're not a good friend, become an enemy. So that also needs to be compromised. So the best things will be more to use the biopolymers. So we're focusing on that as well.
Can I push you a bit further on the previous two questions? Because you put a lot of you put the onus on governments to regulate the disposal, but in order to regulate it, you first need to be able to have an idea of what you can do with the materials. Because you can regulate all you want, but if there's no solution of how to dispose of it. So I'm wondering, is it possible to incorporate this new type of energy storage into a more circular economy approach where you're designing the storage device so all the constituent elements can be reused without loss?
I really don't have answer for that. But for this part, actually, what we are doing now, like I mentioned earlier, like more like a material scientist working on the materials formulation, we can say this can show good properties, good performance, all these things. But we really need to work with what I call like economists and also policy makers how to solve these issues.
No, because I mean, sorry for bringing
Yeah,
it up.
yeah,
This is still very much not a politics or economics problem.
Yeah.
It's like you have the materials and you need the materials to make something, but then how do you, from a material science perspective, deal with the device once it stops being useful? How can you kind of reverse engineer it into, making something useful out of that? Because that's a big part of the problems that we face, that we have that kind of linear throughput of materials, and then at the end of it, we're stuck with something that we can't use. How can we, in a sense, and I think that's also what you were trying to get to, how can we avoid that we get stuck with rest materials that are useless and potentially hazardous?
Okay, one of the things, maybe related to this question as well, one of the things that we are doing with our industry partner, the energy storage devices that we prepare will be sold, for example, in Malaysian currency, like 15,000. Then we sell and use for the electric devices. So normally when you use the new energy storage devices, they perform like 100%. But for electric vehicles, once the efficiency percentage drop to 70%, you cannot use it anymore. You can use it, but the problem is that you have to recharge very frequently. So this becomes like what I call like a disposal. So what we do, because of this can increase the number of disposal things, and these materials can be used for other kind of applications. So for example, like generate electricity in like a small markets, something like that. So initially we sell that, like, for example, like 15,000. So now it will be sold for about like 2,000 or 3,000 like that. So that can prolong the life of the energy storage devices. So that means there is some kind of what I call like other usage as well. But if you just focus on the EV and hybrid vehicles, and the number of things that are going to be trash like this, even huge. So that can be used for other applications as well. Please.
Yeah, I mean, one of the things that I think probably we're all interested in is the way that science can contribute to global problems of resource use, or contribute to the solution to that, which is in terms of when you're picking up your new material, is to have in mind where do those elements come from, for example. So, the massive problem with lithium is that excavating it around the world is basically environmentally catastrophic. And nickel, for example, comes from very specific places, which could have severe political consequences if we become reliant on them. So when you're thinking about which iron should I look at next, you've got your periodic table to choose from. You've got those kind of bigger political things. Well, if I invent a device which is totally reliant on lithium or nickel, then the political consequences are enormous. So how far can you as a material scientist think, okay, I know that iron would be perfect, but actually politically it's going to be problematic. Maybe I should try a different one. Is that something that you think about when you're designing?
Okay, before I come to that point, let me say about the global warming and all these things. So recently I saw a documentary about this, what I call like a scientist about global warming. Then they said scientists work a lot on reducing the global warming and all these things, but they said the global warming happens due to the Russia-Ukraine war compared to what we are focusing on. That many years we work also, we cannot reach to that level, they say. So these kind of consequences are there. And about the materials, when we talk about the materials, like lithium-ion batteries, obviously that's the best because of the lightest element. But now a lot of replacement elements that can be used is sodium-ion batteries and aluminum batteries. So these two things, maybe weight-wise, what I call like more compared to the lithium as an element, but the sodium and aluminum shows good properties as well. So some of these sodium and aluminum batteries, shows better power density and energy density. But in terms of the weight, of course, it is more than that. But we need to find the replacements. So in that terms, it is compromised. So these two are alternative element for lithium.
This might be a silly question. So, given a hydrogel battery, how big a battery would I need to drive a 2-litre engine car?
2 liter.
Yeah, 2000cc.
How big?
Yeah, how big would the battery need to
Remember I showed the casing, right?
be? Yeah.
The casing I showed earlier, it's like this small size.
Mhm.
So now for the, what you call like electric scooters,
Mhm.
so I think maximum you need about 7 for that. So it will be like this big and then this size. And it's not that heavy because of the,
Mhm.
this whole thing is like a plastic casing and then it's not too heavy.
Mhm.
So it's about this big. But you can't use like one portion I told you, so I showed earlier.
Mhm.
It must have like at least like a 7 or 6. Then can.
But they're all in one batteries that you mentioned. So as I understand it, one of the issues with lithium-ion batteries is often they fail when the electrodes start to grow little filaments off of the dendrites, and then that can cause shorting.
Yep.
So do you have the problem when you blend everything together that you're then causing more of that to happen because it's very intimately mixed?
The thing is, first we prepare the hydrogel, and this electrode we polymerize on top of the surface. So far, when we did the SEM and the result shows there is no dendrite formation. So because we are growing on that surface, because they polymerize on the surface. The aniline will polymerize, become like the polyaniline and polypyrrole on the surface.
Does it have similar properties in relation to silicon solar panels in terms of their heat response? You know, performs differently in
Heat.
different temperatures.
For temperature, like one of the part I mentioned, like the thermal stability, because like a normal polymers, so obviously the charging will give a lot of heat, right? So we did the heat stability test as well. So compared to the each polymers actually not, I can say 100%. Like for example, like a polyvinyl alcohol, we can prepare them as a solid electrolyte, and the same polyvinyl alcohol can be transformed to become as a hydrogel polyvinyl alcohol as well, by using like appropriate cross-linking and the temperature and all these things. So when you compare the thermal stability for both of these elements, hydrogel are showing better properties because they can absorb more heat. Because hydrogel, one of the things that we are using as a solvent is water. So water, you know, always can absorb a lot of heat, right? So comparatively with the solid polyvinyl alcohol compared to the hydrogel polyvinyl alcohol, they can absorb more heat. Yes.
Thank you very much for this very impressive presentation.
I need to
especially
say because you need to remember.
the mechanical properties of these hydrogels are very fascinating. And I have a question to the transfer of your results into the industry. Then you have to fulfill these technology readiness levels.
Yep.
And I can imagine that there are also some requirements, for example, that it's not inflammable, but you have organics therein. I have no idea whether this is inflammable or not. Or you mentioned also that this is hydrophobic, so it may attract all the humidity from the air. Are there problems, or what is your solution for the?
The TRL that you mentioned just now, so for the hydrogel, now the TRL level is a TRL 4. So that means because the higher level is a TRL 9, right? So ours reached to TRL 4. So regarding the flammability, of course it's a polymers, the chances are there. So again, because of the thing, we have to check the temperature. So this one, the temperature stability is white. So at that particular temperature, room temperature that we are using, you can withstand. But for high temperature application, depends on what type of polymer we are using. Because there are few polymers, they are thermally stable polymers. So one of the definitions for thermally stable polymers are, they must be thermally stable above 400 degrees Celsius. So if you use that kind of polymers as a host polymer and make them a hydrogel for high temperature applications, then we can avoid the issue. But the polymers that we are using currently stable at room temperature. But at high temperature, it's not so stable. Then we have to modify according to the applications.
I have a question, if I may, and it's not so much about the science of this, which I don't fully understand, but you explained it brilliantly, but I'm thinking about the adoption of technology and wondering whether in terms of diffusing this throughout public and the market and so on, whether or not the positives, the advantages of this type of battery are so great that that would create a demand for these batteries, or whether it would be something that would need to be diffused via things like regulation and industry standards and so on.
So one of the things that we can attract to use this technology is, because the current in Malaysia, for the electric vehicles they're using there, they have a two packs. One is the batteries and supercapacitor. So they have to compromise both that. But with this device, you can use only one. So you don't have these two things. And also the cost of this and that, I got some tables on the cost, but I didn't present here, because the one I want to present the seminars there. So the cost also, you can see, the cost is like a 1/3 about combining these two. So these kind of things can attract the people to go for this kind of a new technology.
Brilliant. Okay, great.
And the cost and also the size is another issue.
That's super, thank you. Do we have some? Please go ahead. You can ask at home.
Okay.
My son.
Regarding this supercapacitor project, I have a few questions to ask. Firstly, between the supercapacitor and the supercapacitors, what are the chemical properties that make supercapacitors have its flaws and allow for the supercapacitor to be able to adapt and defeat those flaws? And the other two questions are, can this supercapacitor project be applied on a global scale in a majority of the global population's vehicles? And if so, by when can this be achieved? And what will the impact be on reducing carbon emissions as a whole?
You don't need any of these with something like that, do you? Difficult question.
So
Tell them to go home.
So the first question is about the chemical.
The chemical properties, and the second and third are, can this be applied on a global level?
No, first question is about the chemical
Yeah.
properties, right? So for chemical properties, like for example, like supercapacitor I mentioned earlier, right? So this supercapacitor will have the combination of both battery type electrodes and the supercapacitor type of electrodes. So when they got these two kind of electrodes, so they can show the properties of batteries as well as the supercapacitors. Maybe not as best as battery, not as best as supercapacitor alone, but when you look at the compromised, so like an easy example, like batteries and supercapacitor is how low. Like one is like you are like a 100-meter runner, so that means you are a very good 100-meter runner. The other person is like a marathon runner. So a marathon runner cannot be a good 100-meter runner. A 100-meter runner cannot be a good marathon runner as well. So when you have these two kind of different things, when it becomes like a supercapacitor, you compromise both. So that particular device become like a more like a have a like a what I call like a sprinting ability and also marathon ability. Might not be top of this, but compromise both values. The second one.
Can the supercapacitor battery be applied on a global scale, as in can it be used in the vehicles of most individuals in the near future, and if so, by when, and how will this impact carbon emissions as a whole?
Okay, so when we talk about these supercapacitor, so that means they actually like in a what do you call like a good directions, but again, for us to become as widely used, need a lot of tests, and then because currently the supercapacitor that's produced in University of Malaya, the lab, already used in electric vehicles in one of the scooter company. So normally what they do, before you use in electric vehicles, the testing ground will be normally scooters, drone. So once all these things well established, then only it will go to the electric vehicles. So hopefully in Malaysia, hopefully in 5 years' time, it can be used in electric vehicles.
Fantastic. I'm conscious of the time with those fantastic questions. Can we talk afterwards? Or is that a quick?
Well, I mean, you seem very focused on vehicles, but it seems to me if you've got a material that can build a solar panel that stores its own energy, the static potential for that is probably more important than vehicles.
Yeah.
So I assume you're also thinking about that.
Yeah, yeah.
Fantastic. Well, thank you very much on those final comments and questions. I think we'll draw to a close. It's been really insightful and really interesting. And as I said, I've certainly learnt a lot, and it's given me a lot to think about.
Thanks
I would like
for
to
an
invite
excellent
Professor.
talk, beautifully illustrated. I love the graphics. And your passion for the topic clearly comes through in your presentation. I'm a professor of climatology in geography as well as being head of Houston. And of course, a talk like this is of great interest to me because I'm a lead author for the IPCC, and of course we're very worried about increasing emissions of greenhouse gases. Battery technology and storage of energy has always been a problem. We have unlimited resources in terms, renewable resources in terms of solar, wind, and many other forms of renewable energy, but of course the problem has always been storage. And tonight I think you've given us an insight into the future, new type of technology for storage. I'd like to thank you for a wonderful talk and for answering the questions. So a round of applause, please.